Hey, what's going on, guys? Good, Mike against here. I'm really happy to see the growing interest around my work and this Bitboard CHESS ENGINE in particular. You guys sending me games where BBC is playing versus other engines, but just in order to explain the confusion you might be getting, like why it's sometimes drawing to with a very weak engines. There are at least two reasons for that. The first reason is that it has a very poor evaluation function, so it's not even about to call this like an evaluation function. It's just the matter of giving an engine an idea of where to develop its pieces. So it's not the evaluation in how it has to be. It's the first reason for that poor results, and the second reason is because without handling the threefold repetition, BBC might find itself in the cases where even being a rook or queen up, he draws the game by the threefold repetition because it doesn't have any idea regarding the threefold repetitions at the moment. So starting from this video, we're supposed to be doing some work to actually solve that, and this work would contain three parts. Well, actually, regarding the particular solving of the threefold repetition, it would contain only two parts. So let me quickly walk through what we're supposed to be doing, and then we'll jump into writing some code. So, in order to identify the repetition of the position, we need to have what is known as the position key or a hash key, and also a hash key or a position key, which might be treated as the unique, well, almost unique position identifier. This would be the U64 bitboard type, by the way, but don't be confused by the name bitboard. It's just the 64 bits long unsigned integer to represent the current chessboard position, and that's kind of it. So there would be two applications for this unique identifier. So first, it would be used for the transposition table, serving the purpose of increasing the performance of our engine even more, even though I'm supposed to be using the very basic transposition table possible ever, because that's, by the way, the very first transposition table I've ever implemented. But what it does at the moment, it just searches faster. That's kind of it. Not really that much, but the performance of like how fast it researches with transposition table compared to without transposition table is well, about the same, like this is happening in Wise, maybe slightly less. I'm using the replacement schema there as described by Bruce Moreland, so that topic is about to come. It would be more didactic rather than for like some real strength improvements, but without those basics we can't really go even further, because transposition tables can have 50 plus tutorials on their own, because that's the really wide there are a really wide range of topics regarding those transposition tables. And again, the second application of our Zobrist keys is actually to detect those repetitions. So you might wonder, and I was actually talking about this as well, that we could have used the transposition table to detect the repetitions, but as far as I'm not really that 100% sure that my transposition table is perfect. Yeah, it works, it saves the notes, it increases the performance, but I'm not really that sure that it is that precise to use it to this important topic like detecting the repetitions. So in case of detecting the repetitions, I would rather try to go the good old way, something like TSCP and Wise do. Even though I've been playing around with this method, and from time to time I'm getting the correct results, like repetition is getting tracked, but sometimes when I'm trying to make BBC playing versus TSCP, sometimes it happens that even being a bishop up in the end game, he still draws the position for some reason. But during it, assuming that he thinks that he's better, obviously. So BBC thinks he's better, and he is a bishop up. Well, TCP has passed pawns, but still BBC considers he's better, but still he draws the position for some reason. And I'm not yet I can't say for sure at the moment whether it's how it has to be or not, so it needs some more research. So by the time that I would have been making this videos on Zobrist hashing, I would have been also struggling to actually get done with those repetitions and finally understand how they work, how the detection is actually working. And then I will definitely make a tutorial on that as well. And as far as we would be able to detect our repetitions, and also we'll have the transposition table as well. At that state, we'll jump into improving our evaluation, and hopefully we would be enjoying the dramatic growth of the actual strength of our chess engine. So without further ado, let's actually go for some basic definitions that regards to Zobrist hashing, how in particular it works, and just go step by step embedding this into our mode generator. Okay, so we'll first write a code right over in here, just right before the main driver, and then I'll put this into a decent place within the source code. So let's try to open the terminal, compile and run the code, so make debug, and if it compiles, I want to run the BBC binary executable, so it should run the search from the previous part, I guess. Oh, it doesn't even go to. Okay, so let's pick up the debugging mode. Okay, we don't need to search the position anymore, so let's just, oh sorry, so let's just print the board and start, okay, and start defining some variables. So we need to hash three kind of, well, let's maybe not three, let's go step by step. So first we need to hash our pieces, and then we need to hash castling rights in peasant square and decide to move 4. Yeah, not 3, they're 4. So I'll now explain what I mean by saying hashing. Before anything else, we need to initialize a few arrays with the random random numbers, and that's the goal for this video at least. So we will have the piece keys. So this would be the U64, right? Because we're supposed to be filling this array with this unsigned long integers. I'm just wondering, when I was doing this, did I actually define that as U64 in my previous codes? Hold on, guys. I just want to check that out quickly. Okay, hopefully I did. Here they are, basically. So let's actually call this random piece keys, and create a variable called piece keys, and the first index is the piece code, and the second index is the square where this piece is actually where it is available. So we have 12 piece types, and we have 64 squares. So that's kind of it. Also, we need to have the random. Well, let's start with in peasant. Random in peasant keys. So this would be the U64 in peasant keys, and indexed by the square. So 64 random number for in peasant to hash the in peasant square. Okay, and also we need some random keys, random castling keys. So we need to hash our castling bits. So the biggest value of our castle bits, assuming that black and white can castle both sides, like king side and queen side, that would be 15 if we just have this number in binary, so everybody can castle anywhere. So in decimal this would be equal to 15. That's it. So we need to define the U64 castle castle keys, and up to 16 elements to match all of those. And also we need the random side key. This would be the only key, and we would be hashing the position with the side only in case if black to move. If white to move, we're not gonna be doing this. So U64 side key like this. And now what we actually want to do, we want to initialize all this arrays with the random numbers. So now they all are initialized to zeros, assuming the GCC compiler runs in programming languages global variable properties. But we need to initialize them all to U64 random numbers. And I'm going to be using the pseudo-random mode generator that we've been creating in the very beginning of this series when dealing with generating magic move number candidates. But anyway, so here we want to init random hash keys. Okay, so this would be the void, right? Void init hash keys. Yeah, because other function would be called generate hash keys. So these are not really the keys. Well, for some reason they call them keys, but well, okay, let's just drop this. So let's leave this standard traditional name basically. So I think this is just fine. Okay, so first we need to initialize this array, so we need to loop over all the pieces, and then we need to loop over all the squares. That's kind of it. So we need to loop over let's say piece codes, to be exact, piece codes. So for integer piece equals to, well, white pawn, and piece is less than less equals. This is incredibly important. I've missed this last equals sign when I was initially implementing this, and had horrible bugs that I had no idea where they come from. So it's incredibly important. Less equals black king anywhere within the source code. Only this like, never this like, only this like. So because we need to include the black king code into the range of the loop over the pieces, so the piece codes, and piece plus plus. And the second thing, the second nested loop would be the loop over board squares. Okay, so we need to say for int square equals to 0, square is less than 64, and square plus plus. And now we need to initialize random piece keys. Probably we don't even need this curly braces, let me see. So I'm referencing the piece keys by piece and square, sorry, by piece and square, and that's basically it. So well, I guess we don't really need this curly braces here. Okay, so just to make sure it still compiles and runs. Okay, so we didn't initialize our piece keys. Well, I can actually, okay, so one more little thing I forgot to do is, before anything else, so here is important thing guys. So I just want to search for random state number. Yeah, this is it. So remember that when we were generating magic numbers for our magic bit boards. I've been using this random state taken from random function of POSIX systems. Well, that doesn't matter where did I take it from. So the idea is to generate pseudo random numbers in the way so they are the same regardless of operating system and execution environment of processor or whatever, basically. So we want to have this random numbers always the same. This was in regards to generating magic numbers, and exactly the same idea here. So at the very end, the particular random numbers we're initializing our keys with should be the same. So those that I have should be exactly the same with those you have, assuming that you use the same the same techniques here. So I need to copy this one, and let me just explain the reason for doing this. This is the safety measure. So if we just go to init all function, so here we have this init magic numbers, which by default is commented and not gonna be uncommented, because we have this magic numbers pre-coded within the source code, and we just save the time on loading the engine. So we want to avoid generating magic numbers from scratch every time, because they would be the same always, and just to save the time we're not doing this. But if for some reason you will uncomment this and then try to run this stuff that regards to initializing the hash keys, in that case you will have a different numbers, and even though that might work pretty fine as well, but just to make sure that regardless of whether this init magic number is turned on or turned off, I actually want to put this random state reinitializing line, let's say update. So even though it most likely it is like this if you didn't change anything regarding this init magic numbers, which we don't really need here, obviously. But I just want to make sure that we're starting generating random numbers using this. Well, I guess this is called seed, if I'm not mistaken. So using this seed. Again, like this line is not necessary, but just for safety measures, just to have the same just to have the same random numbers regardless of operating system and execution environment, I'm doing this. So again, like when I now would be printing some these actual values, well, actually we need to initialize them by the way. So here we want to generate random U64 number. Okay, so this function relies on this seed. That's the idea. So they should be the same. And okay, so well, actually I can need this curly braces actually to embed the print statement for debugging purposes. So let's try to printf, and this would be long hexadecimal. I want to print these keys in hexadecimal, not in decimal, because that makes more sense to me at least. And let's make a new line, and let's print this particular value we're getting initialized. And let's also call init hash keys. Well, actually, hold on a sec, guys. I think I found a better. I call probably, yeah, it's better to call them initialize random keys, because it's not kind of the hash keys. So initialize random keys. Yeah, let's change this to random, and here initialize random keys. Okay. So now I should print some random numbers. Okay, excuse me. Generate random. Oh, get random. Sorry, not generate. Get random number. Okay. So here it generates the random numbers for to hash our pieces later on. So just the array of random numbers. It's the two-dimensional array, but this is how it should be. So what I want to say, guys, so what you need to check and to make sure that is exactly the same like what I have here. So these numbers, you should have exactly the same numbers in case if you're using the same pseudo-random mood generator, pseudo-random number generator I use. Well, obviously you can use the standard C rand function, even though some guys claiming that it's too weak from the randomness perspective. Still, like Bruce Moreland back in those days said that it's pretty fine for him, and he never had a problem with the standard rand function in C. So you're free to use that as well, but don't forget to convert the result to the U64 number, otherwise you will have only the first 16 bits, I guess, being occupied, and the rest of bits won't be occupied actually, which won't work really. So there is some information how to use the standard rand function both in Bruce Moreland's, I don't know, chess program and Wikipedia, but I prefer this sort of same random numbers regardless of operating system, to make sure it works exactly the same in any environment. So I hope this idea is quite pretty clear. So we don't need this anymore. So maybe just to give, well, okay, I thought just to give an extra commentary, but it seems to be redundant. Okay, so let's move further on. So now let's initialize our in peasant keys. So we want to loop over board squares, and I just say for in square equals to 0, square is less than 64, and square plus plus. And here I want to initialize random in peasant keys. So in peasant keys indexed by the square would be equal to get random U64 number, like this. Okay. And we also need the same for our random castling keys. So, well, first the site. Okay, so let's initialize random site key. So by simply saying site key equals to get random U64 number. Okay, and now we need to loop over. Well, let's just call it loop over castling keys, just without those details, like what exactly. Literally, we're looping over the possible variations of castling bits. That's it. So over 16. So int for, let's just call this index, int index equals to 0, index is less than 16, and index plus plus, and here we want to initialize castling keys. So castle keys and indexed by the index would be equal to get a random number, random U64 number, and this should be just it. Okay, so seems to be like this is just fine. Well, probably, yeah, let's just put them in order. So piece keys, then in peasant and castling. In peasant, then we go castling, and finally initializing the side keys. So this to keep this order. Okay. Yeah, seems to be working. So the very last thing we need to do, we need to include this function call into our init_all function. So here we want to initialize random keys for hashing purposes. Okay, so I guess this is it, guys. So I'm just not really showing you like how all the other random numbers look like, because it's literally the same what we had here. So we have all these arrays being initialized with a random U64 unsigned long 64 bits long integers, and that's it. Then we would be using the XOR bitwise operation to actually either add the piece to the position key, the position identifier, also known as the hash key, or using the same XOR method to exclude that from the key. And that would be covered well, probably in the next video. I actually want to, well, probably I would even, I will probably show you this within the next video, and then as far as that would be clear, we'll probably go to actually generating the hash key or unique position identifier from scratch for our current given board position. It would be serving two purposes. So the first purpose is to do this within the parseFen function every time we're parsing uFen, and the second idea is to use this built from scratch hash key for the debugging purposes when we would be incrementally updating our unique position identifiers, also known as hash keys, within our make_move function. So that's kind of the plan. Well, okay guys, so this is it from my side. I hope you learned something interesting out of this tutorial. I hope this is quite pretty self-explanatory regarding what in particular we're doing here, just initializing this arrays with the random numbers and this variable with a random number as well. So it's quite pretty easy and simple. And yeah, so let's say goodbye to each other and see you in the next video. Until that time, and take care. Okay, sorry guys, just a little postscript on video. I've already uploaded this to YouTube, and then horribly realized that actually I'm getting some errors and the code is not getting compiled. So first we have a typo here, so castle should be written like castle, like this. Okay, and the reason for this warnings is because we're initializing our random keys before it has been defined. So I would probably now try to put this code into a decent place overall. So copy, and just wanna call this like Zobrist keys, like this. And the only thing left is actually to take this from here, and well, I'm wondering, so I would be using this probably before the make move, so, or even okay, let me just reference. I'm sorry guys, I don't remember where exactly I did put this. Oh, I'm sorry. Where exactly did I put this code to? So just oh man, if I could only remember. So probably after, okay, bit manipulations, hash keys. Okay, so just right below the bit manipulations. Okay, so let's search for bit manipulations and just right over in here, I'll paste the code that regards to Zobrist keys, and it now should be working, hopefully. Okay, perfect. So now it compiles and runs. So when you're dealing with a single file source code, you always need to make sure that the function that you're calling somewhere should be above the place where you're actually calling this. So that's kind of it. Also, we would be writing the generate hash key function here, and I just want to make sure that this is above the make move function as well. Well, anyway, I think this is quite pretty decent place with the Zobrist keys, because they more like regards to the chessboard chessboard rather than the search in particular, even though they are used in search. So that's kind of it. Okay, guys, sorry for I forgot to do this and said goodbye to you. So I hope now this would be just fine. So never forget to compile and run the code before ending up a video. Okay, guys, so hope to see you next time. Until that time, and take care.